All right, so let's take a deeper look at this kernel tool that we've been talking about until now. And let me quickly remind you that my original hypotheses that we've been looking at for any classification problem look something like this, right? Alpha n star yn, and then the kernel for particular point x plus b star. All right. And how does this kernel work? This x prime works. Well, it computes this z transpose z. So essentially internally, like behind closed doors or inside that black box, what's happening is that this x and x prime, both they undergo some transformation. That's the kernel transformation. And some phi of x or some phi of x prime is computed, which is nothing but my z and my z prime. This is exactly what we get, right? And so essentially my kernel is giving me dot product in some space, which I'm referring to as z space, right? And if we examine the dot product further, right? Dot product is something like this. So let's say my vector z and z prime, and then this is the theta between z and z prime. And so this is essentially z times z prime times the cos of the theta between the two. And if we just like multiply, normalize these, like, let me show you what I mean. So if we normalize this equation here, right? Essentially I'm saying let's do something like this. Get the mod of this dot z prime z prime. So we get this, like, we'll have the only thing that's remaining there will be like cos of these two, right? What does this mean? I mean, of course, like we know all these technicalities, all right? But what exactly does this cos refer to? Now, the cos of theta of z prime, let's assume that's exactly equal to 1. What exactly is it telling me, like just by looking at the picture? Well, it's telling me that the z and z prime are essentially the same thing. Right, they are exactly the same thing. And if my cos theta z prime is -1, these are two different directions, z prime and z, right? So essentially that is telling me something about the relationship between z and z prime, whether they are opposite, whether they are same, how far apart away they are from one another. So this is in some sense depicting similarity, correct? Some form of similarity. I'm not saying that similarity in itself is like one definition for all, but in some sense this is cosine similarity, I can say, right? And so my this kxx prime is depicting cosine similarity, and the kernel which is doing this is computing a measure of similarity, right? So in my final hypothesis, which is like g of x, my kxx prime will find, what does it do? It finds these important points that are extremely essential for my classification problem, and they are the support vectors, right? So basically what I'm doing is give me an input. My kernel is going to compute some similarity with that particular data point, weigh it. So this is my W, so in some sense, not exactly, but yes, some sense like weighing that, and then add a bias to that. So that is exactly what I'm getting here. And if you think about the kernel, it is essentially measuring similarity. It's computing a weighted similarity to these data points that are important, or to the data points that are my support vectors, right? So in general, any inner product algorithm can be kernelized. That means I can have this function that computes the similarity between different points, right? And then I can get results, and that is essentially like a similarity-based method if you think about it. So all we have to do is to design a good measure of similarity, or construct a good similarity measure given my data, given my problem. And once I have designed or constructed that, and somehow like also show that the properties of that constructed kernel or constructed similarity measure has some certain properties, if you remember, positive, definite, and symmetric. If it has these properties, right? And then, of course, like in terms of fitting the data, any linear model should be plausible in that transformed space, right? So then we can essentially utilize all the power of the optimal hyperplane algorithm in any higher dimensional, provided we have figured a way to measure similarity and express it in terms of a kernel. All right, so what are we talking about here? When we started talking about similarity-based methods, if you remember, we thought that that was the simplest thing that we can do in learning. And now, after so much of analysis, after so much of technique discussion from neural networks and variable basis functions to networks rather, to support vector machines, we are back to similarity. So essentially, we are back to similarity-based approach, which can simulate other techniques, and that too optimally. It is doing it optimally, which is like an added advantage. So in like high level intuitively, that is all that is to learning. If you think about it, similarity is all that is to learning, because if there is no similarity of a test point with something, of course, with some definition of similarity, right? If we don't have that, then we cannot for sure say that we have a machinery to efficiently achieve learning. And we do have a machinery now to efficiently achieve that, right? So using these kernel machines, once we have designed them, right, how should we be using them? Like for any general problem, using kernel machines. So the first thing that we need to do for our problem is to figure out, like for any problem, to figure out what is a good measure of similarity. So that's number one. What is a good measure of similarity, which could be different in different problems, which could be different given whatever data we have. And then the second question when designing like our kernel machines is that, will a linear model work in the feature transform space? Right, that's the next question that we should be asking ourselves. Will a linear model, because if we think about all of the problems that we've looked at, essentially coming down to a linear model. So will a linear model work in feature transformed space, right? And then finally, coming up with a good measure of similarity, we can use the support vector machinery to solve any problem. So use the support vector machinery, essentially all the important components of that to solve any problem. All right. Okay, so because we can solve any problem utilizing this approach of first defining a good similarity-based measure depending on the problem, we can apply it to many different problems in different fields. So coming up with good kernel is essentially equivalent to coming up with the right measure of similarity, right? For example, like the inner product measure similarity, which is cosine similarity. And so depending on the problem, we have to determine where we need what kind of similarity. So let's look at these examples that we have. The very first example is about string kernels, an important application when we are dealing with text, when we are dealing with DNA sequences, right? And with almost no effort, we can apply support vectors to like this problem specifically. Uh, to describe this problem, we have like two strings that have some kind of a string composition. And these are essentially sequences. And what we're trying to determine is like if these two protein sequences do the same thing. So how similar they are, how close enough they are to one another. So for this problem, we need to come up with a measure of similarity, right? Maybe occurrence of like some substring somewhere could be a measure of similarity, but then each protein sequence will have like a different length. So maybe like normalizing it in the sense that the longest subsequence divided by the length of the string, right? So maybe longest subsequence divided by the length of each string. So this will normalize the measure because it has to be applicable across all the inputs that we have, right? So we have to be careful in that sense when defining measure of similarity. For example, here, look at this example here, right? So we have like two pieces of text. The first one is, of course, an email that is that looks like some business email where they're talking about some invoice and some other information, right? The other one looks personal, right? A personal message, and this is more like a business message, right? And we are asked to classify this text into two parts. And then we have to come up with a similarity measure and figure out whether they are similar or not, right? So if our classification criteria is to say that whether an incoming email is spam or not spam, right? Then both are not spam, and so yes, um, they are similar because they are not spam. And so if classifying spam versus non-spam was the final goal, then yes, they are similar. But if you want to say whether this is like the defining criteria for the classification problem is business versus personal, then they are different. So they're not similar here. So here, similar or not similar depends on the specific task, even if the inputs are same, right? So that's what this point is trying to emphasize. To design a kernel measure similarity between strings, but then it depends on my final problem as well, right? For example, bag of words, number of occurrences of each atom, co-occurrences of substrings or subsequences, all of these can be utilized to define a similarity measure, but again, it's dependent on what problem you're looking at, what problem at hand is where you are trying to apply that similarity measure. Okay. Another good example, another application of similarity-based application is the graph kernels. For example, performing classification on graph structures, protein networks for function prediction. And then in general, think about these networks that have nodes that represent some user, for example, on Facebook, right? And you have to come up with the right measure of similarity so that you are able to figure out whether we should be advertising or not. So again, it goes inside constructing the right measures, constructing the right features, and then eventually arriving at that, right? Similarity between graphs. So graphs are nothing but nodes, right? So there are many ways of constructing these measures. For example, random walk, connectivity properties, mixing properties. All of these are like some different measures of how we can create these. Uh, Essentially. So this is like another measure between like measuring similarity between nodes, which is a highly popular approach, Jacquard similarity, where we look at neighbors. And of course, this is also used in a lot of applications, but then again, it depends on what exact application are we looking at, and then based on that, decide which similarity measure we need to use. Once we have a well-defined kernel, similarity-based kernel, then we can definitely apply our approach of support vectors. One last example that I wanted to talk about is image similarity. And this is important because if like you're given two images, like of two people, person one and person two, right? And let's say these are like passport size photographs, and we have to figure out whether they are similar or not. So the first thing that we have to figure out is like based on what are these similar? Yes, they are similar because if we are after pictures of humans or pictures with faces, so then yes, they are similar. But if we want to get the identification of a person for some application where we have to do facial recognition, then we need another measure of similarity, right? So maybe we need a neural network to come up with features and then find Euclidean distance between the features and then construct a similarity measure. So it can be like more involved, more complex in that sense. But again, we can, once we come up with my K, I can apply my support vectors and get a good result here, right? And eventually, when we think about the support vectors in general, they are nothing but just a linear model. So that's how powerful a linear model is. And in conclusion, what I like to say is like fancy machine learning is essentially similarity based if you think about it. If you cannot identify the similarity, you may not achieve much, right? The premise of learning is that you can find how similar a particular test point is to some other given data. And this concludes our discussion of support vector machines. Again, repeating, kernel is where all the power lies for the support vector machines, along with the choice of C, which was my regularization parameter, because in practice, we need to be considerate about like how much regularization we need. In all, we have covered radial basis function networks, neural networks, support vector machines, and all of them in some sense are linear models. Uh, Support vector machines are robust linear models, and neural networks are cascaded versions of linear models. So this concludes our advanced techniques discussion. In the next video, which is obviously optional in this course, we'll talk a little bit about pre-processing and some universal techniques that are applicable to almost like all problems. So that's it for this one, and I'll end this one here.